Okay, so time to continue. Today we are continue our lectures on graph theory. So there are some interesting topics. Half of them will be optional again. All the interesting topics are optional. So so let me show you what are the plans. So we are going to look at some very specific graph, maybe the simplest form, called trees. Although it's very simple, it's quite useful in computer science or in mathematics or maybe in biology. The notion of trees was really helpful. Okay, so I want to talk about one particular kind of trees called the minimum spanning tree, and also I'll talk about algorithm on how to find the minimal spanning tree. The algorithm again is extremely simple, but it is extremely useful. I think if you study computer science, you are going to see this many times. Okay, so these are about trees. Then probably after the break, we will talk about this. It's a famous theorem called four-color theorem. I guess most of you have heard of it, but we are going to look at the issues about four-color theorem, and then we cannot prove four-color theorem. You will see the reason, but we are going to prove five-color theorem. we cannot do as best as it can be, but if we just add one more color, we can do it very simply. So you'll see that. Okay, so with this, let's start our lecture. So the first part is to give mathematical definitions of trees. Okay, so here the definition: a tree is a simple graph. Here the simple has a mathematical meaning, right? Simple means no loops, no multiple edges. So graph, graph are a bunch of vertices. You connect them by edges, right? So simple graph, there's a special definition. Says there's no loop, there's no multiple edges. That means between a pair of vertices, you only have one edge. Okay. So a tree is a simple graph that is connected and contains no cycle. There's no cycle, so that's the most important information. It's connected is as you expect, right? So usually when we deal with graphs, we only care about connected graph. In other words, it's just one piece, right? So, but the tree, the most important characterization is it has no cycles. Okay. So, for example, let's see this graph. Sorry, somehow this dot doesn't count. Okay. So this is an example of a tree. You see, it's a graph, right? It's a bunch of vertices that are somehow connected by edges. And then this is simple graph, no loops, right? No loops, no multiple edges. Everything was just very simple. And also it's connected, is in one piece. Again, sorry, this dot, I don't know. So this is connected graph, and the most important thing is it has no cycle, right? So there's no closed loop or cycle. Okay. Now this is okay. Again, I don't know what happened to this dot. So this is another example of tree. Usually, people can draw a tree really like a tree, but here, since we put the tree under the category of graphs, so we just draw it like a graph. So you can, if you want, on the paper, you can sort of like you write something here. Put this one here, and then you go down to here, and then there's a branch. So on the right is here. So, and then on the left, you have a splitting, and then you have several 1, 2, 3. Right? So you can draw it like a tree, and also there's depending on your habit, you can draw the tree upwards, you can draw the tree downwards. So in real life, in biology or in botany, the tree grows upwards. But in mathematics, especially if you work on the whiteboard, you probably will draw a tree from the top all the way down. Right? So somehow you can draw a tree like this, you can draw a tree. So in any case, is a graph like that. Okay, it's very simple. Okay, now let's see some non-examples of trees. So these things are not trees. For example, here, this violates the condition. It has no cycle. You see a cycle here. You see a small closed loop here. So because of this loop, this is not a tree. Right? Now for this, you have the graph is not connected. There's a dot here, then the other one is another portion. So it's not a connected graph, so it's not a tree. The same for here, right? So you can split the graph into two trees. You can think of it as a forest, but you can study them one by one, but we don't call it a tree. Okay, so these are a bad example. These are not trees. Okay. Now we introduce some terminology which are extremely natural. So for example, since we talk about trees, we can talk about leaves, right? So definition, a leaf in plural will be leaves, right? Is a vertex of degree 1. So remember, the degree of a vertex is the number of edges connected to that vertex. So it is a leaf, it means there's only one edge coming in or coming out, going out from that particular vertex. Okay, so let's look at some simple facts. Okay, so there's something called leaf lemma. It says every tree with 2 or more vertices has at least 2 leaves. Okay. Is it easy to see? Okay, so the proof is this. Consider a longest path P in the tree, right? So all our graphs are finite graphs. So for the tree, if it's finite, you can find the longest path, right? So maybe it's not unique, but you can find it. You can find one of them. Now look at the longest path of the tree. Now its endpoints must be leaves. Because why? Because suppose it's not leaf. So it's an endpoint of longest path. Then it has to connect to somewhere else. Okay, so then there are 2 possibilities. One is it is a new node. It's a node that doesn't appear on the longest path. But if you have such a node, this violates the longest path. So you make it longer. So since it's longest path, you cannot extend to some fresh node, right? So that is not possible. And then the only possibility is you connect the node to some node you have seen. Now, if you connect it to some node on this path you have seen, you create a loop. Again, that's not possible. So therefore, if you look at the so-called longest path, the endpoints has to stop there. It is end. You cannot go. So now it has 2 ends. So it has at least 2 leaves, right? So I'll give you an example, like this guy. So what is the longest path? Is this 1, 2, 3, 4? Is 4 the longest? 1, 2, 3, What? Is the 4 the longest path, right? So 4 is the longest path. Okay, so this is the longest path. You can have several, like this is also 1, this is also 1, right? But look at the longest path. Now there's 2 ends, right? It's a finite path, so it has 2 ends. Now I want to claim that these 2 ends must be leaves. In other words, there's only degree 1. So you can only enter and then you cannot go out, right? So let's see. Let me repeat the argument, right? So suppose this guy can go out. Where does he go? So he can go to somewhere else, like here, this guy, so that it is not on this path. Or now, if that's the case, this is not the longest path. It go to something else, right? Now, the other case is he go to a node which is along the longest path. Now, if he go back, then he create a loop. So, create a cycle. So again, it's not possible, right? Or maybe you think this is extremely simple. Then I'm happy. Okay, so the fact is indeed extremely simple. Okay, so this is a lemma which says there are lots of leaves. Okay. Now, let's look at slightly more difficult theorem, property, which we are going to use it later. Okay. So it says this: every tree with n vertices has exactly n minus 1 edges. So this links the number of vertices and number of edges on a tree. On graph, it's not so certain, but on tree, this is the connection is clear. You understand the statement, right? Suppose you have a tree with 4 vertices, and then it can have exactly 3 edges. Okay, so the idea is, well, we didn't learn mathematical induction, but essentially it's mathematical induction. So you are trying to reduce the case to something smaller and smaller, and goes on. So the idea is like this. So we know that there's leaves, right? By the previous lemma, there are leaves. So we delete a leaf from a tree one at a time. So you delete a leaf. A leaf is a vertex with degree 1. So delete one vertex, and then there's only one edge connected to this vertex, right? You delete the vertex together with the edge. So you reduce one vertex and one edge, right? So this is, you delete one vertex and one edge, okay? And then what remains is still a tree, right? Then you look at it, you look at the leaf, you delete one more time. So every time you reduce the one vertex, and at the same time you reduce one edge. So in the end, you are going to delete almost everything until you hit no more leaves. Now, no more leaf means there's only one vertex, because if you have 2 vertices, just now it says it has at least 2 leaves. So you can only get one vertex remain. So that shows there's extra vertex. So right before you reach this single vertex, is one vertex matched with one edge. One vertex matched with one edge. So the numbers are the same. Now in the end you get extra one. So the vertex will have one more. We have one more vertex than the edges, right? So this is again very simple, very intuitive. Okay, so now let's get familiar with some trees. Okay, so let's try this. So I want to list all trees with 5 vertices. Well, let's forget about the unlabeled. So I just want to list all the possible trees with 5 vertices. Now here, allow me a little bit vague. You see the trees, you can draw trees in different ways, but if you can identify them, the fancy word is isomorphic. If they are isomorphic, you treat them as one tree, right? So, okay, so let's just identify what are the trees which look different. Okay. Okay. So according to the solution is there's only 3 types of trees with 5 vertices. Now, can I convince you that these are the only possibilities? Right? You say, okay, oh, I cannot think of, but how do you rule out all other possibilities? So let's try. Let me try, right? Okay, so what do we know? We know that if it's a tree with 5 vertices, it has exactly 4 edges, right? So this is a theorem we know, okay? So now, how can we organize the 4 edges? So we look at the possible degree of a vertex. So the maximum degree it can have is 4. You only have 4 edges, so the maximum degree a vertex can have is 4. So that's the case. So suppose you have a guy which has 4 outgoing edges, then that's the case. You use all the 4 edges. That's the only possibility, right? So if you have one vertex with degree 4, that's here. You have no other ways to arrange, right? You only have 4 edges. They all connect to this guy. So we don't label things. So it's just like this. So that's one case. Second case, we don't have a degree 4 vertex. So then it probably means you may have a degree 3, right? So let's assume we have a degree 3 vertex here. So degree 3 vertex will use 3 edges, right? 3 edges will connect to him. Now there's one more. Now there's one more edges. You can connect it to any of these leaves. You cannot connect to here, because if you connect to here, this guy will be degree 4. So we are in this case. So since this guy is degree 3, so the extra edge can only connect to the leaves here, right? So it's like something like here, right? So that's the second case. Suppose you have a degree 3 vertex, then it has to be like this, right? Okay. So then the remaining case is, oh, we don't have a degree 3. Everything is either degree 1 or degree 2. Now this is the only possibility, because you cannot split. If you split, you have degree 3. So it has to be a line. It's a connected. It's just one piece. So this is the only possibility, right? So no more. So I'm trying to say is there's no other ways to have it. The only challenge possibly is I don't connect here. I connect here. So for example here. But as I said, we look at the isomorphic type or something. So even if you connect here somehow, if I move the paper and by turning it around, it looks the same. So they are essentially the same. Yeah, it's not. Although you can draw it differently, but it's the same tree. Okay. Is this okay? Right. Okay. Now we are heading for the minimum spanning trees. So when I talk about minimum, it means minimum of something. Right? So this about this weighted graph. Actually, we have seen it in the previous lecture. We have seen a Chinese postman's problem. We see a graph that on each pass you have a price, you have a distance associated with the pass. So the weighted graph is a fancy version of saying that. Okay, so let me read the definition from the book. Okay, so a weighted graph is a graph, okay, of course, in which each edge has a number associated with it, which we refer to as the weight of that edge. Okay, so it's very easy to understand, right? So in application, these weights can be cost or distance or traveling time or something. Okay, so we have seen it in the Chinese postman's problem. Now the weight of a graph, of a weighted graph G, is the sum of all the weights. sum of the weights of all its edges. So symbolically, so the weight of the graph is the sum of the numbers you see in the weighted graph. You add all the weight along the edges. So you get the weight of the graph. Okay, so that's some terminology. It's extremely natural, right? Okay, so look at example. So I have this graph, not very complicated, A, B, C, D, 4 vertices, five edges. Now there are numbers. So I have 1 here. Okay, so this edge CD has weight 1, right? There's a number here, and then BD is weight 2. So this is a weighted graph. Now the total weight of the graph, you just add all these numbers. So 2 plus 3 plus 2 plus 3 plus 1, right? So it's 11. Right? As simple as that. Okay, so now we want to look at some examples of subgraphs, and also if it's a weighted graph, the subgraph can also have weight. So we want to define this. Okay, so a subgraph of a graph G is a graph H whose vertices and edges are taken from those of G. So it's just a smaller graph. So you have a big graph, you ignore some parts of it, then you get a smaller graph, right? So it has a fancy name, but it's very easy to understand. So in mathematics, whenever you have a big structure, you could have a substructure. So for those who know groups, so you have subgroup. So for a graph, you have a subgraph. It's just a smaller one, but it's also a graph. Okay, so example. So just now we have this G. G is A, B, C, D. Now I want to look at some of its subgraphs. Okay. So for example, this guy is a subgraph because I just erase one edge, BD, together with the weight. So this is a subgraph. H1 is a subgraph. So the total weight is just, if you add, is 9. Now you can erase some other edges. So you can erase these two altogether. So you get ABC. And then you get another subgraph. And the weight for the subgraph is 5. And similar. Right? So it's BC. Okay, now this is our second main item of today. So we are looking at spanning trees. So here's the definition. You can guess from the name, right? So you call it spanning tree for a reason. Okay. So definition, a spanning tree of a given graph G is a subgraph T, because it's a tree, T for the tree, T of G, which is a tree, and it contains all the vertices of G. So somehow it's like it spans the whole graph. Right? It didn't miss any vertices. Okay, so this is spanning tree. Among all the possible spanning trees, we want to choose something called minimum. The minimum means minimum weight. So a minimum spanning tree of G is a spanning tree which has the minimum weight among all the spanning trees of G. So in this definition, implicitly, the graph G is a weighted graph. So the tree, this spanning tree is a subgraph of G, so it will inherit the sum of the weight, right? So we look at the total weight on the tree, and somehow we select the minimum one among all possible spanning trees. Okay. Example. So here. So look at remember the old graph? So we have A, B, C. Okay, the old graph, we have AD and CD, right? So it's not a tree, it has lots of cycles. Now we want to select a spanning tree. So the spanning tree will be is a tree, and also we cannot miss any vertex. So all the A, B, C, D must be there. Okay, so that's a spanning tree. So it turns out there are 8 of them. So you can you can check, right? So it's not hard because this graph is so small. So you see we have 4 vertices. Any tree with 4 vertices will have 3 edges. So all you need is to exhaust the possibility of putting 3 edges on the tree, on the graph. Right? Okay, so let's look at a few of them. So for example, you can do something like this. So this is a tree. The total weight is 7. Okay. Now you can do better. And this guy, this is again a tree, right? Because it's no cycle, and then the weight becomes smaller. So this is, if you add up, this is 6. Now this is a tree, and the weight is even smaller. It's 2 to 1. It's 5, and so on and so forth. So this is worth 8. So altogether you have 8 of them. So you can have other spanning trees. Okay, so in this example, what is the minimum spanning tree? In other words, which one is the spanning tree having the minimum weight? It turns out to be this T3, right? This guy. The total weight is only 5. All others are bigger than him. So this is the minimum spanning tree. Okay, so now this is a very, very bad algorithm. Or if we want to find a minimum spanning tree. If every time we have to exhaust all possible spanning trees, that's too complicated, right? Even for this simple graph, we have 8 possibilities, and it's not obvious that these exhaust everything. You have to work on it and decide this is really all of them. So is there a general method? Is there an easy method to find one minimum spanning tree? Right. So that's our next topic. Okay. So before that, there's some advertisement. So is why do we care? Well, somehow because you can have real life examples, right? Engineering they care about this. Vertices, you can think of them as houses. In some neighborhood, the edges are TV. And nowadays, it's not TV cables, right? I don't know. Now it's optic fibers or something. So there's something connecting between the houses, and you want to minimize them, and you don't want to miss any house. So you better have a minimum spanning tree, right? Okay, so the edges you can put on the cost, you can put on distance, whatever, to bury the cable and so on and so forth. So the minimum spanning tree would be a subgraph joining all the houses with the lowest total cost, right? So sometimes it is useful. And okay, so all right, so that's why we look at them. Now there in the next 10 minutes we are going to learn one algorithm called the Prim's algorithm. So you'll see his picture in the next slides. So this algorithm is extremely simple. So let me introduce the algorithm first before I introduce Mr. Prim. Okay. So here's the algorithm. So the input to the algorithm is a weighted graph G. Now the output, if you follow the algorithm, in the end you'll get a minimum spanning tree T of G. Okay. So this is the input. This is the output. Okay. Now the algorithm has these few steps. Okay, so the first step is start with any vertex and select an edge having minimum weight among all edges at that vertex. Right? You choose whichever vertex you have. Now look at all the edges coming out from this edge. Select one with the minimum weight. Okay? And then consider all edges that go from each vertex already reached to a new vertex. Okay, so you start from one vertex. You select an edge coming out of this vertex with minimal weight. Okay, so if you are several, you can choose any one of them. So then you choose that edge, you get one more vertex, right? So what you have is a slightly larger chunk of your minimum spanning tree. So now from what you have here, you look at the remaining unreached area. So there are lots of possible connections. So now from all the possible connections, right? So consider all edges that goes from each vertex already reached to a vertex which haven't been reached, right? You will see an example. It become extremely clear. Okay, so you consider all the possible edges. Now you select one that has minimum weight. Okay. Now continue until all the vertices has been reached. So this is the algorithm. Okay. So we'll see an example, and now it's time to introduce him. So he is a American computer scientist. Actually, he's a mathematician and later become computer scientist. Born, I think he's still alive, at least on Wikipedia, he's still alive. So he's born in 1921. So this algorithm actually is discovered by somebody else, Jarnik. He's a Czech mathematician, but he adopted to in computer science. So it got a name, Prim. So some people call it Jarnik Prim, and sometimes there's another one, Dextra. So there are several names. Never mind. So it's the same algorithm. Now this algorithm is a typical example of something called the greedy algorithm. So I don't know in engineering you've seen it. In computer science, this is very common. So the greedy algorithm, what does it mean, greedy? Greedy means greedy. So we want to find, for example, we want to find minimum of something, right? So in the end, we want to find the minimum. So the greedy algorithm will say, at every step, you try minimum. So let's use the word global and local, right? So in the end, I want to achieve globally minimum. Now, the greedy algorithm will say, don't care about the global thing. Every time you try to minimize what you have so far, right? So you locally, you always minimize. Now, if the greedy algorithm works, the local, if you always pursue the local minimum, in the end, you can achieve global minimum. So this is greedy algorithm. But there are also examples. The local minimum doesn't work. Somehow you chase the local minimum and it turns out you pay more. So life is like that. But in some cases, the greedy algorithm works. Right? So this is just one example. So you probably, the same apply to maximum. You want to reach the global maximum. You always want to maximize your I don't know, personal wealth. So the greedy algorithm will tell you that at every step, if you can maximize your next step profit, you maximize it, right? So that's the greedy algorithm. Whether it works depends on situation. Sometimes it works. Sometimes, like if you maximize it, then you have no follow-ups. Then actually it's not the global maximum, right? Now, suppose here you take less, and then there are lots of futures, and then maybe in the end you get more, right? So greedy may work, may not work. But in this simple case, the minimum spanning tree, this greedy algorithm works. Okay. Okay. So finally, I want to repeat: this is a simple algorithm, but extremely useful. All right, so let's use an example to illustrate this algorithm. Okay, so this is example. So apply Prim's algorithm to this graph, starting from vertex A. Okay, so let's try to be as greedy as we can, right? So starting from here, I have 3 possible edges. Now, every step I want to minimize. Right, so this is the meaning of greedy. Okay, so I'm at A. There are two edges with weight 1. These are the minimum, right? So I don't care. You can choose anyone. Okay, so let's see what okay, so here, starting from A, we look at all possible edges, right? So these are A, B, A, C, and A, D. Now, two of them are having minimum weight, A, C, and A, D. So the algorithm allows us to choose either one. I don't know what he chose. So, oh, he chose AC. Okay, so it doesn't matter. AD would be the same. Okay, so he chose AC. Okay, so now the graph says this. So there are some notations. So the boxed vertices means we have covered, we have seen these. These things are already being considered. And these double lines indicate the edge we have selected. Okay, so we will never change. Once it's in, we never erase and change our mind. Okay. So here we have considered vertex A and C. We determine choose this edge AC. Okay. So these are we have seen. These things are not we have not seen. So we have to look at all possible connections between what we have seen and what we haven't reached. Right? So we have to. So this part is what we have seen. Now these parts are what we haven't reached. So we look at all possible connections. So B to A, B to C. Okay, all these are the possible ones. These two are not. These two are between the unseen. Right? We haven't reached there. So we look at the edges that join a vertex that has been reached, which is the boxed guy, to a new. New means these unboxed guys, right? So there are 5 possible connections. These 5. Okay, what is the weight of this? 3. Right? This guy is 3. This weight is 3. Sorry, missed the number. Okay, so there are 5, 1, 2, 3, 4, 5 possible connections. Again, we will be as greedy as we can, right? So among the 5, which one is the minimum? Well, there's a 0 here. So this is the minimum. So we have to take this. Okay. So the minimum one is CD. So we take CD. So we have now the current tree, the spanning tree grows a little bit to cover vertex D, and we have 2 edges. Okay. So these part are we have seen. Now the unseen part is B and E. So now we look at the connection between what we have seen and what is outside. Okay, so here we have ACD now as the things we already reached, and then the edges that join a vertex has been reached to unreached vertex are these. Okay, so we have seen these. So these 4 red vertices are the new connections, right? So again, we have to be as greedy as we can. So here is the weight 2 edges are the smallest, right? So we choose any one of them. I don't know what he chose. So okay, among these edges, the ones that minimum weights are CB and CE, right? CB and CE, they are of weight 2. Okay, both choices are allowed by the algorithm, so we choose one, let's say CB. Okay, so he chose CB. So he has this. Now you can guess, right? So we have seen this part. There's only one vertex we haven't considered. So we look at him, look at all possible connections, choose the minimum one. Okay. So now we have seen these. So the candidates are these 3, right? These 3. And then we will be greedy, so we will choose this one. Okay. So that's. So in the end, the output of Prim algorithm is A, C, B, D, E, and the total weight is 1, 0, 2, and 1. So this is 4. Okay. So this is the algorithm. Very, very simple, right? Oh, so here's exercise. Apply Prim's algorithm to the same graph starting from vertex B. Okay, so I guess we okay, so I hope the annotator still works. So you help me, right? So let's choose one. Okay, choose this with my favorite color is what? I don't know, green. Okay, so does it work? Okay, so we have to start from here, right? So we have 3 edges coming out. Select the greedy, right? So we select the minimum one, is this one. So we are here, right? Okay, now from outside, what are the things connected to the green part? So there are 3. There's 2, there's 2, 3. So you have to choose obviously one of the 2s, right? So we have to take this one. I don't know which one you want to take, BC or CE, I don't care. Okay, so choose BC, okay? And then there are AD, which is we have to consider. So look at all the possible connections from AD to the ugly part I have drawn, right? So these 3. So there's this one, the AB, AC, DB, DC, DE, right? This is 0, so this is the minimum one. So I take this with that. Okay, and then only A is left, so there are AB, AC, and AD. So you can choose either this or that. Again, we don't care. So we choose, let's say, select A. We choose this, for example. Right. So this is the algorithm finishes. We have a spanning tree. What is the total weight? 1 plus 2 plus 1 plus 0. So it's still 4. Right. Not very surprising, right? So, okay, so that's the prim algorithm. Okay, so this is simple. I think there's one more, and we have time to do one more. Okay. This one. Okay, let's try it one more time. So apply Prim's algorithm to the following graph, starting from vertex C. Okay. Hopefully my favorite color green is still here. Okay, so start from here. Okay, so several edges coming out. Choose the one with the minimum weight. No choice here, just this one. Now, among all the possible edges connecting to B and C, you look at the smallest one. 0, right? So this is definitely, so we take this. Now, there's only one way out, so you don't have any choice. You go here. And then what? Then look at all possible edges connecting to the green. Okay, so this. So 3 seem to be the minimum, right? So we circle this and get that. Right? Is it right? So now there's only one F left. So we look at the ways to include F from the green area. So we select F, no difference, either CF or EF. I don't care. So maybe CF. So this is one of the minimum spanning trees. Okay, so it's quite easy, right? Okay, good. So okay, so let's take a break, and then after that we talk about something more difficult. 4 colors here. Okay, so a break. Okay. Just now there's some concern about history. Well, so this algorithm has many names. So we call it Prim's algorithm. But okay, let's assume Wikipedia is right. Sometimes it is wrong, but I have no other sources. Okay, so the Prim algorithm. Okay, so there are several names. If you look at the boldface things, okay, this Dijkstra, and the concern was, okay, Dijkstra is also a famous computer scientist. So there are lots of algorithm was named after him or him and other people. So this is one of the examples. So it's called the Prim Dijkstra algorithm, or you can say Dijkstra Yarnik Prim. So there are lots of names, and very often it's just called greedy algorithm. So it has lots of names. But anyway, so this is, since some of you are concerned about this, so let's. Okay, so now let's go back to our graph theory. Okay, is this the one? Okay, I hope I don't need annotator. If I need it, I'll use it. Okay, so now we are looking at this. What? Hmm? Yeah, so now we are looking at something more interesting and more mathematical, even philosophical. Okay, so here, so we are talking about something called four-color theorem. There's some history here. Okay, so it has relative long history, right? So it went back to 1852. And then there's a guy called Guthrie, was trying to color the map of counties of England. So he's English. Now he noticed that only 4 different colors were needed. Okay, so I didn't type all these things. So you color a map, right? So you have a map of England there. And then the map of England was divided into different portions, counties. So you color each county by a color, but you don't want to color the neighboring counties using the same color, right? So that's the basic rules of coloring maps. So he discovered that only 4 different colors was needed. You don't need 5. Okay, so he was wondering if this is a general fact. He asked his brother, okay, whoever he is, and then his brother probably cannot solve it. So he asked his teacher, De Morgan. Not De Morgan, right? We know the De Morgan's law, and De Morgan cannot solve it. So and then it's okay. So then several wrong proofs of this 4-color conjecture was given over the years. So for example, there's a proof given by Kemp in 1879, but then an error was found a few years later by someone else, Hewood, Percy Hewood. And then building on Kemp's work, Hewood showed actually 5 colors can work, right? So the theorem says every map in the plane can be colored by 5 colors. Again, this is general education, so I didn't state the exact statement. For example, the map, right? You should not allow what is it called? So there's one country, but they have several pieces. We don't allow that. So you just there are some conditions, but let's forget about those small prints. So basically, the map, if you just color map in a plane, you only need 5 colors. Okay, so this is simple enough. I'm able to show you in the remaining half an hour. Okay, but how about this 4-color theorem? So this turns out to be extremely difficult. So finally, the four-color theorem was shown by, okay, actually there's a long history. So this is from 18 something, and then we jump to 1976. Okay, so the four-color theorem was shown by Apple and Harkin. They are from University of Illinois, Urbana-Champaign. So after they proved the theorem, they say at that time they still send mails. So the mail, there's a chop that says 4 colors suffice. So the university was very proud of their achievement. And okay, but this proof, their proof, has some controversy. So why? Because their proof need assistance of the computer to verify a large number of cases. Okay, especially at 1976, the computer power was not very, okay, so it's just by brute force. They divide the case, the graph, into some, they call it critical cases. So if you can color all the critical cases, and then you can show the theorem. But it turns out there's about 2,000 critical cases. And if you use a pen to study the cases, it takes a long time. So 2,000 cases will take forever. So they use computer to verify the 2,000 cases. It's 1,000 something. It's less than 2,000. So the computer verify them. They all work. So, but it's at least at that time, or even a few decades after their proof, is still not feasible to check. Recently, I think they are, well, not recently, maybe in the recent years, people have simplified it, and the computer power is also increases. So there's no controversial. The proof is definitely correct. So four colors suffices. Now, why this is even philosophical? So the four-color theorem is one of the first examples people prove using computer assistant. Okay, and then this is a typical example when people discuss the meaning of mathematical proof. Right. So do you consider this as a proof? So somebody show you that, okay, I have a proof, right? You just ask computer to check these 10,000 cases, and then computer can help you. So do you consider this as a proof? Well, then people will think, what does a proof tells us? Do I learn anything from the proof? No, it's just the stupid computer just check we don't learn anything, right? We probably learn the theorem is true, but usually we believe the case, right? So there are debates of what is the meaning, what is the purpose of proof, and why mathematicians sometimes prove a theorem over and over again, because each new proof bring you new insight, right? So, but then how do you define insight, and so they become a philosophical question. A more recent interesting example is this Kepler conjecture. Again, it's people use computer to prove it, and then there's some controversial. But 3 years ago, the author somehow developed. He has a team. He developed another algorithm, so that he's very sure that there's nothing wrong with his computer-aided proof. So it's no longer controversial anymore. So I think with this AI or with computer power, right, getting more and more, this computer getting more and more powerful, or this AI getting more and more advanced, we will see more and more examples of computer-aided proofs. So whether this is good or bad is up to you to decide. Okay. So it's an interesting phenomenon. But unfortunately, my knowledge is not enough to prove 4-color theorem, so I'll prove the 5-color theorem. Right? Hopefully, I'll convince you 5-color is okay. Again, this is optional. Any proofs are optional, so this is for fun. Okay, so first we have to turn the map into graph, turn the problem into a vertex color problem, so that something we are more familiar. Okay, so we have seen in the bridge when we talk about Euler circuit, right? So we turn a map into a graph, right? So over there is if two region was joined by a bridge, you add edge, right? Now here, sorry, let me repeat again. Remember in the bridge problem of the 7 bridge in Königsberg, there are several lands, right, connected by bridges, separated by rivers, right? So we want to turn this into a graph. So each piece of land become a point, become vertex, right? So the vertex are connected if there's a bridge, right? So in this case, it's not a simple graph. You may have several bridges link the two vertices, right? So that's what we have done over there. Now in this problem, again, we use the same idea. So we look at two regions. So if they share a border, we'll add an edge, right? So if say Singapore and Malaysia, they share a border. So if Singapore is a vertex, Malaysia is another vertex, we add an edge of between Singapore and Malaysia. So last time we talked about proper vertex coloring. If you have an edge, the two sides you cannot color by, if it's a proper coloring, you cannot color them by the same color. Now it translates into you cannot color the two countries using the same color on map, right? So I'm trying to say there's a very natural transformation from the coloring map to coloring the vertex of a graph. Okay, so now here, but there's an extra condition. Not every graph can arise from a planar graph, a planar map. So I'm trying to say this. So from a map, you induce a graph, but not every graph was induced by a map, because some graphs are so complicated, it does not come from a map. Forget about the planar. So just it doesn't come from a map. So we call a graph which arises from a map a planar graph. So what is a non-planar graph? You cannot, if you draw the graph on the paper, piece of paper, some edges has to cross. Then this is not a planar. So let's try this annotator again. Activate. Okay, so how to have a is this the way? How to have an empty page? Come on, I just want to have a page. Oh, good. Okay. So let's see. So I can draw a graph like this on the plane without edges. Okay, so these are the 4 vertices, and then I connect it this way, right? So everything fits well on the plane. So this is a planar graph, okay? Now let's try to add one more edge, right? So if I add an edge between the two, it looks like I have to cross. Sorry, if I add another diagonal, it looks like I have to cross, so I violate the planar. But however, I can connect them using this, right? So then I have, so this says K4 is planar. K4, remember K4 is, the graph is 4 vertices. Every pair of vertices is connected. So K4 is still planar, but K5 is not. So suppose you have 5. Now you can connect some of them. This one, maybe you can connect like this. Connect like this. Oh! These two, I think, no matter how hard you try, I don't think you can. So you have to cross, right? Either you cross here or you cross with the other one. So K5 is not. Okay, so so the example shows there are graphs which are so complicated that you cannot draw it on the plane without crossing the edges. So the but however the graphs coming out of induced from a map, they are all planar. Okay. So I don't need this anymore. How do I go back? I don't want this, I don't want this. Okay, yeah. How come I get this? I used get the full screen. Why the full screen like this? Well, okay. Never mind. I can. But I want full screen. Yes. Yes, but still, it's less full. Never mind. I will not use an annotator anymore. You can quit and. Don't worry. Good. Okay. Anyway, so let's continue from here. Sorry about the. Okay, so I just explained that not every graph is planar. Okay. So now we move on to the next item. So recall the chromatic number chi of G of a graph G is the minimum number of colors used to have a proper vertex coloring, right? So on both ends of an edge, you cannot color by the same color. Okay? So the four-color theorem says for any planar graph G, the chromatic number is less than or equal to 4. 4 color suffices. Okay? Good. So now we want to prove the 5-color theorem. Now, to prove that, we need to use a tool. The tool is only used at one step. But however, the tool is interesting. So I want to introduce the tool. But however, the tool has a small catch. Okay, so I'll try to cheat you as far as I can, right? So if you agree with me, then we just go to the end. If you catch me, then I'll see. Okay, so here, so there's a formula called Euler formula. Okay, so the Euler formula, okay, the same Euler. Okay, so the Euler formula says this. So let G be a connected planar graph with n vertices, m edges, and L faces. But here I cheat a little bit. So the faces, the faces stands for the areas. So for example, this white area is considered as one face. This triangle in the middle is another face. This is another face. This is another face. This is another face. But the catch was the blue one, the outside one, is considered as one face. So the why we have this not so nice presentation? Well, the original Euler formula is talking about polyhedrons, right? So the polyhedrons is a three-dimensional object, and it has vertices, edges, and faces. So the Euler formula originally applied to the counting of things related to polyhedrons. So we want to use it to describe planar graphs. So you have to open up. Imagine you have a polyhedron. Then you have to stretch one face so that you can draw it on the plane. Think of a cubic, right? So there are two faces. One is probably facing me. The other one is facing you. So if I want to draw a cubic on the plane, I have to open up the face, not open up, and stretch it, the face which is further away from me, so that I can draw it on the plane. So that face will be the infinite face we are talking about. So that's why this is a little bit not so clean. Okay, anyway, so hopefully the rest is all right. Okay, so we have L faces. The formula says there's a relation between them. So the number of vertices minus number of edges plus number of faces equal 2. This is actually a fantastic formula. Okay, so the proof, well, they are proof by mathematical induction, whatever. So I took one proof on the internet. It has some story, or it's easy to describe. Okay, so let's follow the proof on the internet. So a typical planar graph looks like this. Okay, so the white dots are the vertices, the black things are the edges, the white things are the faces, but the blue one is also a face. Okay, so that's the picture, a typical one like this. So think of the infinite face of the graph as being the ocean, whatever. So probably the guy who invented this from Dutch, I don't know. So or Singapore, right? So we are in the middle of the ocean. Okay, so the edges of the graph are being dikes made of earth. So the faces of the graph, other than the infinite face, are the dry field. Okay, so just some story. So now, when a dike, such as the one with red, was breached, right? Suppose it's broken, and then the water will come in to flood this face. Okay, so the mathematical way is, if you remove this edge, you remove a face. It's just as simple as that. Okay, so but let's follow that story, right? So somehow the water comes in through this edge, so then you get something flooded here. Okay, so you have one red edge and one face was flooded. Okay, now keep doing this. So then the water can come in here, can come in here, come in here, come in. So keep doing this. Imagine that in the end you flood everything, right? So the red edges are indicating where does the water comes in. For example, here the water first come to occupy this face, and then continue to occupy the triangle in the middle here, and then continue move up to occupy that. So you sort of remove 3 edges, you also remove three faces, right? So the picture is you do this until you flood every area, so then you get a tree. So the resulting graph of the black edges, the red are the guys you remove, or you think of the water comes in. The unbreached dikes are the black ones. So they form a spanning tree of the original graph. Just believe this. Okay, so now what is the total number? So the total number of edges of the graph is the total number. Okay, so it's a sum of the red and the black, right? So it's a E red, E for edge. The red edges, number of red edges plus the number of black edges. Now, how many red edges? Well, we have a correspondence from the red edges with the number of faces, except the ocean. So the number of red edges is equal to the number of flooded areas, which is L minus 1, because L also includes the ocean. So that's why it's L minus 1. Now, how many black edges? Now here we have to use this tree theorem we learned. So the number of black edges, because it's a spanning tree, so is equal to the total number of vertices minus 1, right? We said that. Okay, so now you plug in this, the M equal E red, which is L minus 1, plus E black, which is N minus 1, so is N plus L minus 2, right? So that's the proof of Euler's formula. Okay. Now, we need Euler's formula. We don't need the full thing. We need Euler's formula to get here, to get this. If G is a planar graph, then there's a vertex with degree less than or equal to 5. If you believe this, you don't need Euler formula. So we need Euler formula to do that. So let me fill out the steps. So first, from Euler formula, we get a property about why is type plane? The planar graph. So the planar graph has a property. So a planar graph with n vertices has at most 3n minus 6 edges. So why? Let's see. So it gets most edges if every face is a triangle. So because if you have a polygon as a face, you can keep adding edges so that you can have more. Now, if it's maximal, then every edge will be every face will be triangle. So let's do this. So let's take a planar graph with maximum number of edges, and then every face is a triangle, right? Otherwise, you can add edges, you can increase it. Okay, so now if every edge is a triangle, it means you count the number of, so each face will give you 3 edges. But however, the neighbor face, each edge was counted twice. So 3L equal to 2 times M. Think of it, right? Every face is surrounded by 3 edges. So each face contribute 3 edges. Now, however, two faces are sharing the same edge. So the same edge was considered twice. So it's like our proof of handshake lemma, right? So we have 3 times L, which is the total number of edges together with each edge considered twice. So 3L will be 2 times M. Okay, now once you have this, then the formula is easy. Then you use Euler's formula. So you know that the L is 3/2 times L. What I'm doing? You eliminate L, right? So L is 2/3 of M. So replace L by 2/3 of M, simplify, you get m equals 3n minus 6. So that's the maximum number of edges you can have. Okay, now the next reasoning is if G is a planar graph, then there's a vertex with degree at most 5. Why? Because otherwise, every degree will have at least 6. Every vertex will have degree 6, right? More than 6. So by handshake lemma, we know that 2 times the 2m is bigger than or equal to the sum of the total degrees. Now the sum of total degrees is bigger than or equal to 6 times n, because you have n vertices. Each vertex has degree at least 6. So you have this is bigger than 6n. So then you get m is bigger than or equal to 3n. Right? But we know m is at most 3n minus 6. So that's not possible. Right? So this the whole slide just I'm trying to convince you, if G is a planar graph, it has a degree less than or equal to 5. Actually, some planar graph can have degree 5. If you can show that, actually there are examples. Otherwise, 4-color theorem will follow. Anyway, so, sorry. From this slide, I don't care whether you get the proof or not, you have to get this fact. There is a vertex with degree at most 5. Okay, so now our proof will be quite easy. So let's prove this 5-color theorem. Okay, either you prove by contradiction or you prove by mathematical induction. But since I didn't talk about induction, I'll try to use the language of proof by contradiction. Okay. Okay. So suppose you have a graph which is not 5-colorable, right? So then there's a smallest one in terms of vertices. Okay. So let G be the smallest planar graph in terms of number of vertices that cannot be colored by 5 colors. So now we want to show something is wrong. Okay. Okay, so by the previous slides, we know there's a vertex with degree at most 5, right? So from the previous slides. So let's look at that guy. So this is the white guy here. Okay, so this is the guy. The degree is at most 5. Okay, so there are 2 cases. One is the degree is less than or equal to 4. The second case is they are exactly 5. Okay, in both cases we get something wrong. Okay, okay, so suppose the degree is less than or equal to 5. Now imagine you take away this, from the graph you remove this guy together with these edges. So the remaining part can be colored with 5 colors. Right? So the remaining part can be done by 5 colors. Okay. But there are only 4 nodes connect to this V. No matter which color you have here, you can use the 5th color to color V, and still a good coloring. Are you with me? Sorry. Think of you have a gigantic graph, a gigantic map, right? You color with okay, gigantic graph. You want to color it. Now look at this node. This node has degree 4. Okay. Imagine, forget it for a second. Then we get a smaller graph. Our graph is the smallest possible graph, which cannot be 5 colored. So after you remove this, you get a graph even smaller. So it can be colored by 5 colors. Okay, color it by 5 colors. Okay, now put this V back. The 5 color coloring the remaining ones can only have this situation. So because it has 4 neighbors, each neighbor can use 1 color. So you can only use 4 colors around this V. And then you can use the 5th color to color V, and then there's no problem. Right? So the G, our graph can be colored by 5 colors. So there's something wrong. Right? So So this is the argument. So let's see. So there are at most 4 colors that has been used on the neighbor of V, right? So there's at least 1 color that is available for V. So G can be colored by the 5th color. G can be colored with 5 colors. The contradiction is because you assume G cannot be colored by 5 colors. So now you can, right? So that's the easy case. Now the second case is the V may have 5 connections. He has 5 neighbors. Now we still want to say that we can somehow manage to color it with 5 colors. Now the obvious way doesn't work because the 5 neighbors can, okay, so the obvious way says this. We remove V for a second. We can color the remaining one using 5 colors. Okay, color them. And then look at neighbors. Oh, but maybe we are not so lucky. All the neighbors are colored by different color. So to color V, you need 6, right? So that's the worry. But now we try to somehow massage this graph so that change color, cheat here and there, so that we can do it. Okay, so here are the steps. Okay, so that's our case 2. The degree of V is 5. Now, as we argued before, taken away the vertex with the edges can be colored, the remaining graph can be colored by 5 colors. Okay? So if 2 of the neighbors of V are colored with same color, and then then you only use 4 colors to color his neighbors, and then you can color V with the 5th color. That's the lucky case. That's a simple case, right? So there's a color available. No, then we are done. So we may assume that all the vertices that are adjacent to V are colored by 1, 2, 3, 4, 5. Right? Let's say in this order. So this is V1. This is colored by 1, which is red. The guy is colored by 2, which is blue, and so on and so forth. So there are 5 colors used to color his neighbor. Now we have to do something. Okay, so now let's consider all the vertices being colored with 1 and 3, and all the edges among them. So you look at, so here the order is important, right? We order them, this is 1, this is 2, this is 3. So we consider the vertices colored with color 1, the red, and 3, which is yellow. So there are lots of them in the graph. So let's consider all of them. Now, together with the edges, for example, in this in this graph is, so we have considered this, and something here. This, and something there. Right? So we consider all these, the graph using the first color and the third color. Okay, so we consider them. 2 possibilities. If this subgraph G is this subgraph of G, is disconnected. Suppose the picture is like this. It's like this. You don't have, so this part and that part are not connected. They are separate. There's no connection. Okay? So then what you can do is, okay, so suppose this subgraph of G is disconnected, and V1 and V3 are in different components. And then we can switch the color 1 and 3 in the component of V1, right? So here, it used to be red, yellow, and something else. Now just swap yellow and red, right? So change this to yellow, this to red, this to yellow, this to red. So it's still a legal coloring. It doesn't, right? You use 5 colors. It doesn't matter. Red has to go to this, right? So as long as it's a coloring, is fine. So you do this. You swap the red and yellow in this component. It's still okay, right? So the result is this guy become yellow, and then he become red, right? So you do this. So if you do this, you have red available here, right? So you can switch the color 1 and 3 in the component of V1. so that V1 become yellow. Okay, so this will be a 5 coloring of G taken away of V. Furthermore, V1 now is yellow, is color 3 in this new 5 coloring, and V3 is still yellow. So color 1 is available for V, so you can color V as red. Right? So this is the first case. The components are disconnected, so there's no connection. Now, how about they are connected? So you have something like this, right? You look at all the nodes and edges which colored with red and yellow, and then they give you a continuous. They give this one piece, right? So it's like something like this. Okay, so therefore V1, V3 must be in the same component in that subgraph. In other words, there's a path from V1 to V3 such that every vertex on the path is colored with either 1 or 3, right? Something like this. So you cannot do this cheating. If you swap and then the yellow, the red is still here. So, right? Okay, so what do we do here? So in this case, now we consider, so now we have this curve, the red and yellow surround here. Now we consider the other pair, this V4 and V2 and V4. Okay, so we want to do the same thing, right? So you look at a subgraph generated by using color 2 and color 4. Okay? Now the situation is, because you have a closed curve here, and V2 is inside the curve, the curve, V4 is outside. So they cannot be connected. If you connect it, then it's not planar. Sorry. Being planar means there's no edge cross. So here, it's guaranteed the component containing V2 and the component containing V4 has to be disconnected. Here we use our intuition. The theorem is Jordan curve theorem, but anyway. So if you have a region, 1 point in the region, 1 point outside region, you cannot connect them without crossing the boundary, right? So I guess we don't need to prove it. Actually, it's a deep theorem, but are you with me? So we do the same thing for V2 and V4. So now V2 and V4, the subgraph they generate cannot be connected. So we can swap the color. So for example, we change V2 to green now. So then the blue is available. Sorry, what is original? Right, original color is V2 is blue, V4 is green. Okay, so now we look at the component containing V2. So we swap blue to green, green to blue. This is still a coloring, but we have 2 green connecting to V. So the blue is available, the deep blue is available, right? So you can color this guy using deep blue. So this is a good 5 coloring. So again, we can color the graph G with 5 color. It's again a contradiction, right? So therefore, no matter what situation we are in, we always get something funny. So it means we are able to color the graph using 5 colors, right? So that's the proof. If you are interested in this, we can talk, right? But the idea is like this. So the 5 color theorem is not hard at all, but 4 color is extremely hard. Okay. So next week we will move on to coding or something, to a completely new topic. Okay. Okay. See you next week.